This video is about potential dividers, which really is the culmination of our understanding of electric circuits. If you think about a really basic circuit that we started with at the start of electricity, so we have a power supply and we have just two identical bulbs. Okay, we had this situation and we maybe said, for example, that the EMF of the power supply would be 6 volts. So if these two bulbs are identical in their resistance, then the voltage would split evenly across them, so each would have a potential difference of 3 volts. Now, that situation is fine when we make the assumption that they're identical, right? So really what we're saying when we say they're identical is that resistance is the same, okay? However, what happens if these two bulbs or any components aren't the same? And that is how potential dividers work. So when we draw potential divider circuits, a potential divider circuit is really straightforward. Okay, now I'm going to just show this, and I'm going to just call this voltage in, okay, because this could be connected straight to a power supply, or it could be part of a bigger circuit. So we have a voltage coming in, and these just show two terminals, so just imagine like two wires maybe connected to a power pack, right? But that bit really isn't important for this. The bit that's important is this bit, that any potential divider circuit is basically just consists of any two components which have resistance in series with each other. So if I start off with two fixed resistors as an example, okay, so I'm going to call this resistor 1, I'm going to call this resistor 2. If I was to put a voltmeter here, and I'm going to call this voltmeter 1, right, I would be able to measure the potential difference across R1. If I was to put a voltmeter here, I'm going to call that voltmeter 2. That would again give me the potential difference across R2. So what I want to be able to do is to work out the voltage across any one of these components at any time, right? Now, because these two components are in series with each other, the thing that we know that is going to be the same for both of them is both R1 and R2 are both going to have exactly the same current, okay? So the current in the first resistor is going to be equal to the current in the second resistor, which is also just going to be equal to the total current that is going around the circuit, okay? So what I can then do is I can say, well, because the current in each of these things is the same, I can say, well, rearrange Ohm's law to give me current. So current is voltage divided by resistance. And I can say, well, if the current in both of these two things is the same, then the voltage across resistor 1 and the voltage across resistor divided by the resistance of resistor 1 will be equal to the voltage or potential difference across resistor 2 divided by the resistance of resistor 2. Now what we then tend to do is we tend to rearrange this equation and add it into the equation for the total current, because the total current is going to be linked to the total resistance. Now because this is in series, the total resistance is R1 plus R2. Okay, so if I use this equation as total, so we've got the total voltage, which is actually the voltage going in. Okay, the total voltage, the voltage going in, is going to be equal to the total current, which we know, because these two things must also be equal to this expression here, times the total resistance. Okay, so what I can do is I can substitute in my total current for this expression. Now quite often what we have is we'll rearrange this so that I have maybe one of my voltages, and I am only interested in working out one of my voltages, and I will end up by rearranging that equation, and I'm not going to show you how to do this because it's something we'll do in class. You end up with this equation, right, which is I'm going to use V1. So V1, which is the voltage across that, is going to be equal to R1 divided by R1 plus R2 times the voltage that goes in. Now, this equation may look complicated, but really, if you look at this bit, all you are doing is you are saying what ratio of the total resistance is R1. So this is just a fraction, right? So you're working out what ratio of the total resistance is R1, and you're timesing that by the voltage that comes in to give you what ratio of the voltage is R1 going to receive. So let me put some numbers on to make a little more sense. So let's just say the voltage going in is 9 volts, and let's just say that for argument's sake, this has a resistance of 3 ohms, and this has a resistance of 6 ohms, okay? So, if I wanted to know the voltage across R1, I would do the resistance of R1, which is 3 ohms, divided by 3 plus 6, which is obviously 9. So 3 divided by 9 is a third. And I'm going to times that by the voltage going in, which is 9. So a third of a 9 is 3 volts. Okay. If I did the same for V2, then it would be 6 divided by 3 plus 6, which is 9, times 9 would be 6 volts. Okay. So that should be fairly obvious numbers to you, but this works for any more complex situation. So let's look at a more complicated one. So we've got our voltage coming in, and this time, just to prove that this works for any two components of resistance, I'm going to make this a thermistor. Okay, so I've got a thermistor with 1000 ohm resistance, and I have here a fixed resistor which I'm going to say is 500 ohms. Okay, and the voltage coming in is 25 volts. Okay, so just completely made up numbers. Now, what we need to do is we need to use our equation. If I want to know the voltage across this component, then I just need to know, as long as I know my resistances, I can work that out. So it's going to be V1 is equal to 1000 divided by 1000 plus 500, which is 1500, times 25. So let's do that. 1000 divided by 1500 times 25, and we get 16.6 recurring volts as our voltage across my thermistor. If I did it for V2, it would be 500 divided by 1500 times 25, and that would give me, and I don't necessarily have to do this calculation again, by the way. What I could do is I could go, well, I've got 25 volts going in. I'm just going to take away, if 16.6 volts are going there, whatever's left is going to be, what's the voltage here? But let's just prove that. So first let's do it this way. So 500 divided by 1500 times 25. So we get 8.3. Okay, and just for the sake of proving this, if we do 25 minus 16.6, you get 8 point, and this was 8.3 recurring. Obviously I put 6.6 rather than 6.6 recurring, that's why it's come out as 8.4, but you see that it comes out as effectively the same number. Okay, so either of these methods could be worked. And this is also useful because if you've done this, you can then say, for example, what happens if the temperature of my thermistor increases? Well, that means this number, my resistance, is going to decrease. So if the resistance of this number decreased here, and this number is obviously staying the same, that means that the total resistance is going to drop, and it will mean that the voltage across this component is also going to drop. The voltage across this component is going to increase. So potential dividers are really important to understand. They're really useful because they don't require you to know necessarily the current all of the time to be able to work out things that are useful. Having the current is no bad thing, because what you could then do is, for example, for each component, what I like to do is to write this next to each component and to fill it in so I know what I'm calculating. So I know, for example, this is 500. let's say I've worked out the current, or I've been told the current over here is like 3 amps, just as an example, then I could work out what the voltage would be just using Ohm's law, and I wouldn't have to use the potential divider equation. So if you don't understand potential dividers, just go back, watch the video again. Don't worry too much about this section here, okay, and being able to work out where this equation comes from, right? The key idea is that you just understand that because this is in series, that the current is the same for both of them. And so because the current is the same for both of them, if the resistance of one of these things changes in some way, it will affect the total current in the circuit because we're changing the total resistance, and that will therefore affect the voltage across each one. So it's really the understanding behind the maths that you need at this level. You will in class look at how we get to this equation from here, but the main thing is understanding that key idea that because any two components in series with resistance, the ratio of their resistances will determine the ratio of their voltages, and that is what a potential divider circuit is all about.